Good afternoon, guys. Welcome back. Today we are going to be talking about um, work and power and energy. We started our discussion of work last time, but we're going to continue that today and talk about how work is related to both energy and power. If you guys remember last time, we defined work as a force that was applied through a distance. But there is a secondary way that we can define work. Work can be thought of as the energy that we have transferred to a system or from a system, um, which is another way of saying that the work that we do can be thought of as the change in energy that we have done to a system. If I've added or taken energy away from a system, then I've done work. Okay. We can also define energy as the ability to do work. And I want you to notice that we've used the term energy to define work, and we've conversely used work to define energy. That is because, as we're going to see later, work and energy are really the same thing. All right, they are really two peas in a pod. Now, typically, the easiest way to relate energy and work is to talk about things in a mechanical sense, in a physical sense. Um, Mechanical energy is the energy that is possessed by an object either due to its motion or energy that's stored in an object because of its configuration or its position. Um, the reason why we typically use this kind of energy when we're talking about work is because this energy is more tangible. We can see it, we get a better sense of it. It's not the only kind of energy, but it's just easier for us to um, calculate. It's easier for us to get a sense of. Mechanical energy typically comes in one of two forms. It's either kinetic energy, which is the energy of moving objects, the energy of motion, or potential energy. Potential energy is either the energy that we store in an object due to a result in the change of its position, or it could be because of the elastic nature of an object. We change the shape or configuration of an object. Imagine a spring that we either compress or stretch or twist. We've changed its shape or configuration, and as a result, we've stored energy in that object. Okay? Now, there are lots of different kinds of energy, lots of other forms of energy. In fact, we typically talk about 6 different forms. We'll get into the specifics of those other 5 types down the road. But just to make sure that everybody understands all of those types, remember that we could be talking about thermal energy. Sometimes when we do work to an object, we change its temperature. We could be talking about electromagnetic or radiant energy. Um, this is really light energy. And when we do work to an object, we could make it produce light, either light in the visible sense or light that is radiant that we can't see. When we do work to an object, we could make it generate wave energy. Mechanical waves are the kind of waves that you can see, where material is actually moving up and down, perpendicular to the direction or parallel to the direction of travel. So things like waves on the ocean or sound waves. Okay, we could be talking about doing work to a system and storing energy in the form of a chemical bond. Okay, chemical energy. The reason why we eat our food is because we're extracting the chemical energy stored in the bonds. And lastly, we could describe energy from a nuclear sense. Nuclear energy, or what's also called atomic energy, is the energy that is stored in the nuclei of atoms. We can extract that energy by either taking multiple nuclei and fusing them into a single nucleus, or splitting an atom. When an atom undergoes fission, it will liberate energy from its nucleus. We'll talk more about the specifics of each of those down the road. Okay, so remember that in the world of physics, work has a very specific fixed meaning. Okay, for us to do work, there has to be some kind of measurable change in that system. Okay, we have to actually make it change, and we have to make it change with the force that we apply. So imagine that you are pushing on a brick wall. If that wall doesn't move due to your force, then you haven't done any work to it. Okay, the only way that you're going to actually accomplish any work pushing on that wall is if that wall changes in some way, shape, or form. Okay, you could make it move faster if you applied enough force to it. Maybe you could. You might change the shape of the wall. You might tip it over. You've got to make some kind of change occur with that wall before you've done any work to it. Okay. Okay. So let's talk about that concept of work again. Just to reiterate, remember that work is defined as the force that we apply to an object that causes a displacement. And mathematically, we expressed that work as W is equal to F times D. Now, there's a little bit more to this that we need to consider. And if you remember, we talked last time about the fact that the force we apply to the object has to be parallel to the direction of motion. Okay? Any force that is not parallel and it is instead coming at some kind of angle is going to have an impact on the total amount of force that is being used to do that work. And that's where our trig functions come into play. Okay, in this case, we're talking about the cosine of angle theta. Now, those of y'all that are in geometry right now, you'll be talking about your trigonometric functions, sine, cosine, and tangent, a little bit later in this semester. Okay, but for now, I want you to think about this from the standpoint of Pythagorean theorem. Okay, and that's what I want to do on the next slide. Okay. Just in terms of terminology, just so everybody's on the right page, remember that F represents force in the equation, D represents displacement. For our purposes, we're going to assume that distance and displacement for now are the same. And then this symbol right here is a Greek uppercase theta. And that typically just is a representative of an angle, any kind of angle. Just like in your algebra class when you use X to represent an unknown, we use theta to represent angles in geometry. And as a result, we use it in physics as well. So let's look at a couple of examples of that, okay? Imagine that we have some kind of cart, and we are applying 1,000 newtons of force to that particular cart. Well, if we know how much force we've applied, and we also know the displacement, then we could easily calculate the amount of work that we've done, okay? Pretty straightforward. But what happens if we apply a force and we are applying that force at some kind of angle? Okay, in this case, our angle is right here between horizontal, which is the direction that we're moving this object, and the length of this string or rope or chain, whatever we're using to move that cart. Now I want you guys to remember that the motion of this cart is going to be horizontal. So the only force that we need to consider in our equation is the force that's in the horizontal direction. Okay? In this particular case, we are applying a force of 5 newtons on this cart. But the only force that's in the horizontal direction is this force of 4 newtons. Okay? Now, if we change this angle, even if we kept the 5 newtons of applied force the same, then our functional force here would change. If I made this angle less, then this force would go up. if I made this angle bigger, then this force would go down. Okay? And for those of you all that are in Algebra 2 this year, you already know, if you're in geometry this year, you will learn that if we are talking about the cosine of an angle, all right, as theta decreases, the cosine of theta increases. All right? So as this angle right here gets smaller, the cosine of that angle gets bigger. And in fact, the cosine of 0 degrees is equal to 1. All right, now let's think about what that means for a second. If I'm applying 5 newtons of force to this particular cart, and I'm applying that at an angle of 0 degrees, then 0 degrees, or the cosine of 0 degrees, is 1. And in our equation, since W is equal to F times D times the cosine of our angle, we already know that our force is 5 newtons. And it doesn't matter at this point what our D is, but our cosine is equal to 1. Okay? Which means, really, that of the 5 newtons that I'm using to push this object, I'm getting all of it out to do my functional work. Okay? If this angle is anything above 0 degrees, then this value right here would get smaller. And as a result, this leg in my right triangle is going to get smaller. If my 5 newtons were up like this, like that, then the horizontal component of that is going to get a lot smaller. And as a result, I'm not going to be doing as much functional work. Okay? All right. So, let's look at this. Remember that W is equal to FD times cosine of our angle, where W is our work, F is our force, D is our distance or displacement, and theta is our angle. So let's apply this to a real circumstance and see if we can get to the bottom of what's going on. Let's imagine for a second that we've got a box that has a mass of 15 newtons, a mass of 15 kilograms, and we are applying a force to it of 100 newtons. Now, our example says that we're going to push that object 5 meters. Okay? It also says that we're moving it horizontally 5 meters. Okay? So we're moving it. The motion is in the exact same direction as our force, meaning that theta, in this case, is equal to 0 degrees. And when I calculate my work is going to be equal to F times D times the cosine of theta. So in this case, we're talking about 100 newtons times 5 meters times the cosine of 0, which is going to be equal to 100 times 5 times 1, or 500 joules, Newton meters, if you will. It should be an M. Okay? All of our force was in the functional distance, so we extracted all of that out to do work for us. Now, on the other hand, let's assume that we've got some kind of string attached to this object and we're pulling at an angle of 30 degrees. Okay? Now, if I draw a vector diagram for this, we can see that the functional force is in that direction. Okay? That is the force that matters right there. The component of our force that's in the vertical, okay, we'll call this part of the force F of x because it's in the x direction where we're trying to move, and this force is in the y direction. The F of y force isn't going to do anything for us because we're moving this object again horizontally. Okay? So our work is again equal to F times d times the cosine of theta. So in this case, we've still got our 100 newtons of force. We've still got our 5 meters. But now we've got an angle of 30 degrees. All right. And that's not right. I'm on radians and not degrees. Give me 1 second. Yeah, there we go. All right. So in this situation, we've got our 100 newtons times 5 meters, and the cosine of 30 degrees is 0.87. Which means that instead of doing 500 joules of work, we've only done 433 joules of work, or Newton meters. Okay? By using this angle, we reduce the amount of functional work that we were actually accomplishing. Okay? All right. Now, in the last example, we've got a completely different animal altogether. All right, now we are actually lifting up this object. And to lift up that object, I have to apply a force that is at the very least equal to the weight of this object. Not the mass, but the weight. Now, if you remember, weight is the same thing as the force of gravity. And like any force, weight is equal to mass times acceleration. In this case, our acceleration is equal to acceleration due to gravity. So the mass of our object is 15 kilograms, and our acceleration is going to be that due to gravity, 9.8 meters per second squared. Which means that our object has a weight that is equal to 147 newtons. If I don't apply at least 147 newtons to this object, it's not going to go anywhere. Okay? So at the very least, I've got to apply that much force to move this object. Okay? Remember that in example 1 and 2, I'm working against friction to move it horizontally. But in example 3, I'm working against gravity, which is why we've got to use our acceleration due to gravity. All right? Now, remember that gravity is straight up and down, and my force is applied straight up and down. Okay? So work is still going to be equal to F times D times the cosine of my angle. My force is now 147 newtons. My distance is still 5 meters. And my angle is 0 degrees. because I'm applying my force in the upward direction and I'm moving the object in the upward direction. And we just discussed the fact that the cosine of 0 degrees is 1. Okay. Which means to lift that object up, I'm going to have to do 735 joules of work, or 735 Newton meters of work. Okay. All right. So let's talk about power. All right. Power is defined as the rate at which we use energy. But remember that energy is the ability to do work. So if we call power the rate at which we use energy, it can also be described as the rate at which we do work. Now, like any rate, rates are dependent upon time. So power can be thought of as either the work divided by the time or the energy divided by the time. They are both going to give us power. So either work divided by time or energy divided by time. Since work is force times distance, we can think of power as force times distance divided by time. I want you to notice that when we do that, we get something a little bit unusual. All right. Since power is equal to force times distance divided by time, we can really just isolate this as one term. And distance divided by time is equal to velocity. So power can be also thought of as force times the speed, or the force times the velocity. Okay. Now, this is going to allow us to have a variety of different complex units. Okay. Remember that force times distance is a Newton meter or a joule. Okay. So since we are dividing Newton meters or joules by seconds, power can be thought of as a joule per second. Since force is kilograms times meters per second, and distance is meters, and time is seconds, then we get this complex monster right here. You can see how our power units start to get really convoluted depending on how we look at power or how much we simplify it. The easiest way for us to think about this is Newton meters per second or joules per second. Okay, force times distance divided by time, or energy divided by time. Now, none of those are really simple. So scientists simplify all of those into a watt. When you describe a joule per second or a Newton meter per second, that's really the same thing as a watt. Okay. Yes, just like your appliances at home or your light bulbs, when you read that light bulb and it says that it's a 40 watt or a 75 watt light bulb, that is the number of Newton meters per second that light bulb is using. Okay, or the number of joules of energy per second that are being dissipated by that light bulb. Let's erase that. Okay, so you guys might not even remember the space shuttle because it's been a long time since those flights actually occurred, but this is the space shuttle right here. The power that it puts out is unfathomable, and we'll describe that here in just a second. Again, power is thought of as the rate at which we are doing work. How fast are we doing work? Since a single watt is not much power dissipated or energy dissipated, we typically either describe power in a a prefixed unit like kilowatts per hour, or perhaps megawatts or gigawatts. But when we're talking about reasonably low power outputs, we typically talk about horsepower. And a horsepower is just that. It is the power, the average power of a horse. Okay, and the typical horse can generate about 745 watts on a consistent basis. Okay, if you were to put out 100 joules of work in a second, that's 100 watts. Okay. Another example, if you run upstairs and you're 70 kilograms, that would mean that you've got a weight of about 700 newtons. Again, your mass times acceleration due to gravity. And if a typical flight of stairs is about 3 meters high, then that means that to go up that flight of steps, we take your 700 newtons, multiply it by the distance you moved to get 2,100 joules. And if you did that in 3 seconds, 2,100 joules divided by 3 seconds is 700 watts. Okay? Now, I will tell you that running up a flight of stairs that's 3 meters high in 3 seconds is a monumental task. So for you to maintain that for an extended period of time, it would probably be unrealistic to think that you could generate 700 watts. Okay, normally we would do a lab on this very thing, but we're not going to get a chance to do that this year. The space shuttle puts out several gigawatts of power, and it does that for about 12 minutes going into space. It's pretty amazing it's able to put that out. So let's look at a couple of these power calculations real quick, and then we'll wrap things up. Okay? All right. So imagine that you've got a 5 kilogram cart that you push with 30 newtons of force against friction, meaning we're pushing it horizontally, and we do that for a distance of 10 meters in 5 seconds. If we determine how much power we're putting out, remember that power is equal to work divided by time, and work is equal to force times distance divided by time. If we know the force is 30 newtons, and we know the distance moved is 10 meters, and I can plug those in for force and distance. And then if we know the time is 5 seconds, then I can multiply my values on top to get 300 joules, divide that by my 5 seconds, and we're looking at 60 watts. Okay. And that's what will show up here. Okay. A couple more advanced examples of this. Oops. Here we go. Imagine a hydroelectric power plant that drops 20 meters in total with a flow rate of 2,000 cubic meters per second. And we want to figure out how much power that thing puts out. Well, a couple things we need to know. We need to know how much water we're really dumping in terms of weight. How much does 2,000 cubic meters of water really weigh? Well, 1 cubic meter of water weighs 1,000 kilograms. All right, so if we're calculating the weight of that, remember that weight is equal to m times g. So our mass is 1,000 kilograms. Multiply that by acceleration due to gravity, and that's how we get from 1,000 kilograms to a weight of 9,800 newtons. Okay? So that is the force of that water. Okay? Now, that's happening every second. Okay? That's happening every second. So again, if power is equal to work divided by time, then the work that gravity is doing is going to be equal to that force, the weight of that water, 9,800 newtons, times the distance that it's being moved, which is 20 meters, every 1 second. Okay? Oh, and the one thing that I forgot there in my calculation was that we calculated the weight of 1 cubic meter of water. But we're talking about 2,000. So we would have to multiply that value by 2,000 to get our final product here. Okay? Sorry about that. Another example. Let's assume we've got a car on the freeway that is moving at a velocity of 30 meters per second. And it's doing so at a force of friction of 1,800 newtons. Okay, so again, remember that power can be thought of as force times velocity. So in this case, we've got our force of 1,800 newtons times our velocity of 30 meters per second. We're still talking about Newton meters per second, even if we do the calculation this way. Okay? So that's going to be 54,000 joules. Okay, that's a lot. Okay, it takes a lot to keep a car going that fast. Okay, 30 meters per second is about 70 miles per hour. And then lastly, consider cycling up a hill that's got an incline of 10%. It's about a 6% grade, or a 6-degree slope, I should say. And we're doing so at a velocity of 5 meters per second. Okay. Well, again, if we've got our angle of 6 degrees, then we're trying to raise ourselves up. Okay. Which means that the angle that we're really talking about here is the difference between this one and 90 degrees. If I draw a picture of what that's going to look like, if we've got a road surface that's horizontal like this, and our angle is there of 6 degrees, remember, for that cyclist to actually do work, they've got to lift themselves up that way. So the angle that we really care about is this one up here, not that one. Okay, so if this is 6 degrees, that angle's got to be 84 degrees. Okay, so work is going to be F times D times the cosine of our angle. And F times D is really the same thing as M times G times D, since F is really the same thing as M times G times the cosine of our angle. Okay. Lastly, we would have to divide that by our time, okay, which would simply be that. All right. The other way to consider this is since power is equal to force times velocity, and we already know our velocity here, we would simply incorporate that cosine of our angle into this equation. We just need to make sure that we're using that 84 and not 6 degrees. Okay? All right. So to summarize, remember that work is a force that causes change in a system. That change could either be that the system gets faster, or slower or changes direction. It could be that we're pushing the object, but it's moving at a constant velocity. So energy's got to go somewhere. It could go into changing the temperature of that system. We could change the height. We could lift that object up by doing work to it. We could actually make that system produce light. Okay, for instance, if you're rubbing your hands together and sliding them past each other, you're doing work because your hands are moving. But when you stop, your hands aren't moving any faster than they were before, and they're not any higher. Instead, we're actually producing infrared radiation. We're producing light. We could actually produce electrical charge by doing work. Imagine rubbing your feet on a carpet in the wintertime and getting a static electricity charge being built up. Okay, that could be the work that you did. Okay. Remember that energy is the ability to move. We're going to move something. We're either going to move a large-scale object, or we're going to move heat from one place to another, or we're going to move electrical charge from one place to another. Okay, we're going to do something. Okay, and then lastly, power is the rate at which we are either doing work or dissipating that energy. Okay. Thank you guys so much. I appreciate it, and we'll see you next time.